Hello, this is Skill 7.4, and in this lesson we're going to talk about inverse functions, or more generally just inverses. So a definition is that an inverse relation is a relation that interchanges the input and output values of the original relation. Okay, interchange is just a fancy way to say switch around. Input is your x, and output is your y. So basically, when you do an inverse relationship, you're switching around your x and y. So if I look at these first few examples, we're going to take an equation and we're going to find its inverse by switching x and y around. Okay, so I'm going to rewrite this as x equals 7y minus 4. And then I'm going to solve this for y. So I'm going to add 4 to both sides. Okay, that gives me x plus 4 equals 7y. And because we're not done solving for y, I need to then divide everything by 7. So we get y equals x plus 4 all over 7. Now when you look at this, hopefully you notice that the operations that were in the original problem are reversed in the inverse. So notice that we had a 7 being multiplied to x. Now that 7 is being divided. We had a minus 4, and in our inverse we have plus 4. So just kind of think about that as you're doing these if you're trying to verify if you did it right. All right, let's try the next one. On the next one here, we have f of x, which, by the way, f of x is the same as saying y equals. So if you see that notation, just remember f of x is the same as saying y equals. So we're going to swap our x and y around. And because we have a fraction here, I like to go ahead and clear them out. So I'm going to multiply the entire equation by the denominator of that fraction. So I get 5x equals y plus 10. And I want to solve this for y, so I'm going to get the y by itself by subtracting 10 on both sides. And I get y equals 5x minus 10. And if we were to double check with our original equation, originally we had x being multiplied by a fifth, which is the same as dividing x by 5. So now we see that the x is being multiplied by 5. What might be weird here is we see the plus 2. Where's the minus 2? Well, that's because we had modified the equation by multiplying the whole thing by 5. Okay, so that's why you see it as such. I will do example 3, but I am going to skip the challenge one. Not because we can't do it, but I'd rather just show that to you live in person. So I'm going to show you the third example here so that you can see an example that isn't linear. So on this one, again, make sure you switch your x and y around. And then you're going to solve for the new y. So we take away 3 on both sides. And we get x minus 3 equals y squared. And since we don't want y squared, but rather we want y, we have to take the square root of both sides. Square root cancels with the square, so we get that y is just square root of x minus 3. All right, so that's how we do it with equations. Okay, now let's talk about what happens to the input and output. Let's see what goes on here. So we have a couple of equations, and I have the x and the y's. I'm plugging in some x values for my first equation here, the y equals 1/2 x plus 7. Notice that I used x values that were multiples of 2 because our fraction has a 1/2 in it. So when I look at plugging in -4 for this x, half of -4 is -2. -2 plus 7 gives me 5. When I plug in -2 for my x, half of -2 is -1. -1 plus 7 is 6. If I plug in 0 for x, half of 0 is 0, plus 7 makes 7. And then I plug in 6 here. Half of 6 is 3. 3 plus 7 makes 10. okay? All right, so now if I look at y equals 2x minus 14, 2x minus 14 is going to be the inverse of the equation that we just had. So what's going to happen now is I'm going to use what were my y values from the equation I just did. Those are going to become my x values in this new situation. And I'm going to plug those in for x and see what my y values become. So if I plug in 5 for x here, I get 2 times 5, which is 10. 10 minus 14 is negative 4. If I plug in 6 for x, 2 times 6 is 12. 12 minus 14 is negative 2. When I plug in 7 for x, 2 times 7 is 14. 14 minus 14 is 0. And finally, when I plug in 10 for x, 2 times 10 is 20. 20 minus 14 is 6. So when you look here, notice that on the original equation, the 1/2 x plus 7, our x values were what we were given, and then we got our y values. In the inverse, so this is the inverse, notice that the x and y's just switch spots. So what does the domain and range of a relation and its inverse do? The domain and range switch. Remember, domain is x, and range is y, and they switch. Okay? So just keep that in mind. That is what inverses do. Now, how do we look at it from a graphical perspective? We can use something called the horizontal line test to help us determine if an inverse relation will also be a function. You may remember that in general, to check if something is a function, you could use the vertical line test, and the vertical line test has to pass in order for something to be a function. So like, for example, if I had a graph like this, and I were to use the vertical line test would pass because no vertical lines would cross through this graph in more than one spot. Well, for us to have an inverse, since x and y switch, what's the opposite of a vertical? It's going to be a horizontal line test. So what we're going to do to determine if an inverse is also a function is use the horizontal line test. Now when you look here, you can see that I have a horizontal line that goes through many points. So this example of my green graph would not have an inverse that is a function. Okay, it'll have an inverse, it just won't be a function. All right, so in order for an inverse to also be a function, your graph has to pass the horizontal line test. So it says the inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. All right, so let's look at an example. So let's say we have the equation y equals negative 2x plus 4. Well, hopefully you know from our parent function conversation that this is a linear equation. So if I were to graph this, we are going to start at the origin, and we have a plus 4, so we're going to go up 4. And our slope is negative 2, so that means I'm going to go down 2 and right 1. And I'll just do that many times. We see that it is a line, and I cannot seem to connect those very well. All right. Oh, shoot. Anyway, so we draw this line, and when we look at that line, the question is, does it pass the horizontal line test? So if I draw horizontal lines, will there be a horizontal line that goes through the graph more than one time each horizontal line that I draw? And hopefully you can see that that would not happen. So that means we have an inverse. Since the graph passes the, by the way, horizontal line test, I'm going to call that HLT from this point on. Since it passes the horizontal line test, the inverse will also be a function. Okay. Can you think of any of our parent functions where it would not pass the horizontal line test? Hopefully you realize that examples that won't be functions if I have a quadratic, that will fail. If I have a, let's see, what would be another one that we've talked about? Absolute value would be another one that wouldn't. Okay. So those inverses will not be functions. All right. Okay, so now let's talk about determining if things are inverses by using compositions, okay? So if we do that, an inverse function says the original relation and its inverse relation whenever both relations are functions, okay? The functions f and f inverse, so by the way, this notation right here, if I can just highlight that, this is the same as saying f inverse, so inverse of f. It does not mean f to the power of -1. I know it looks like that, but it means inverse of f. And if you compose the function with its inverse, you should get x. And if you take the inverse function and compose it with f, you should get x. Okay? All right, so what we're going to do is we're going to use our composition, what we learned last time. We're going to use that to help us verify that this f of x and this f inverse of x are in fact inverses. Okay, so I'm going to first look at f of f inverse of x. So I'm going to take my outside function, which is f. F is 7x minus 4. And I'm going to replace that something with my f inverse being this equation. So we have 1/7 x plus 4/7. Okay? Now when I distribute here, 7 times the 7th, the 7's will cancel, so I get 1x. 7 times 4/7, the 7's cancel, and I just get plus 4. And then I can see the plus 4 and the minus 4 cancel out, so all I have is x. Woohoo, that means we have inverses. Those are inverses. We can also do this the other way around. If I did f inverse of f of x, well, my f inverse function is 1/7 something plus 4/7. And I'm going to replace that something, the input, with what f of x is, which is 7x minus 4. And then I'm going to distribute. So 1/7 times 7 is just 1x. 1/7 times -4 is -4/7. And then plus 4/7. And you can see now that the -4/7 and the +4/7 cancel. So we just get x. And as long as your compositions result in x, then you have inverses. Okay? All right, last example. For this one, P of x is defined as these ordered pairs. And if I asked you to tell me what P inverse of x is, I would just switch the x and y ordered pairs. So that's going to be your P inverse. Sorry that took so much space there. So if I want to find P of 2, I'm just looking at my original P function. Look where x is 2, its y value is 4. P inverse of 4, well, I need to go to what I did in part A, because that's my P inverse. P inverse of 4 gives me back to 2. P of P inverse of 4, these are inverses, so that will just equal that 4 that we got. P inverse of P of 2, these are inverses, so that'll just equal 2. P of P inverse